Welcome to lecture 5 on measure and integration. If you recall, in the previous lectures we have been looking at the various classes of subsets of a set X with various properties. We looked at what is an algebra, what is a sigma algebra, and a monotone class. Today we will start looking at functions defined on classes of subsets of a set X. We will look at first what is called set functions, and then we will look at a very important example of a step function, namely the length function. So let us start defining with what are called set functions. Let us start with C, a class of subsets of a set X. Any function mu, so this is a Greek symbol called mu. So a function mu defined on the class of subsets C of a set X and taking non-negative extended real valued functions. So this interval 0 plus infinity both included denotes the set of all non-negative extended real numbers. So a function mu defined on this collection C of subsets of a set X taking values in non-negative extended real numbers is going to be called a set function. So it is a function whose domain is a collection of sets. That's why it is called a set function. Next we will be looking at some special properties of, we will be analyzing such functions. So let us define a set function mu, of course where C is a collection of subsets of a set X and 0 to plus infinity the non-negative extended real numbers. So a set function mu is said to be monotone if it has the following property, namely for any two sets A and B in C, mu of A is less than or equal to mu of B whenever A is a subset of B. So it's some kind of a monotone property that whenever A is a subset of B and both are in the collection C, we want that mu of A should be less than or equal to mu of B. So this is called the monotone property. Next we look at what is called finite additivity property of a set function mu. So a set function mu is said to be finitely additive. So I am emphasizing the point finitely and additive if it has the following properties, that mu of union of sets ai I equal to 1 to n. So given any finite collection of sets a1, a2, an in C, we want mu of the union of these sets is equal to mu of ai's. Of course this will be whenever a1, a2, an, this is a finite collection of sets in C such that their union also belongs to C, for otherwise this number on the left hand side of this equation will not be defined, and we want further these sets are pairwise disjoint. So ai intersection aj is empty for I not equal to j. So once again let us see what is finite additivity. Finite additivity means for any finite collection of sets in C, a1, a2, an in C, such that their union is also an element in C and these sets are pairwise disjoint. For any such finite collection of sets, we want that mu of the union is equal to summation of mu of the individual ai's. Intuitively keep in mind mu in some sense is denoting the size of a set A. So we are saying mu of the union is equal to sum of the individual sizes whenever the sets ai's are disjoint, and this is we are requiring it for any finite collection I 1 to n. So in a1, a2, an is any finite collection of sets in C which are pairwise disjoint and such that their union is element in C. We want mu of the union is equal to summation of mu of the individual ai's. So such a property is called finite additivity property of mu, or one says mu is finitely additive. We can extend a generalization of this definition. We will say mu is countably additive. So from finite we are going to countably additive if mu of union an's 1 to infinity is equal to summation of mu n an's Of course, whenever A1, A2, An is a sequence of sets in C such that their union is also an element of C and they are pairwise disjoint. So countable additivity is a property about a sequence of sets A1, A2, An so on in C which are pairwise disjoint and their union is an element in C. Then we want for any such sequence of pairwise disjoint sets, mu of the union must be equal to summation of mu of Ans n equal to 1 to infinity. There is another notion of called countably subadditive if mu of A is less than or equal to summation 1 to infinity mu of Ans whenever A is a set in C and A is contained in union of Ans where Ans also in C for every n. So in some sense if A is covered by a union of sets Ans, then we want the size, so that is mu of A, to be less than or equal to summation mu of Ans n equal to 1 to infinity. So this is called countable subadditivity because here we are just saying that mu of A is less than or equal to, and we are not requiring that Ans are pairwise disjoint. So this is called countable subadditivity property of the set function mu. A set function mu is called a measure on C, where C is a collection of subsets on C, if mu has the property that it is countably additive. So it should be countably additive and we want that empty set belongs to C and with the property that mu of empty set is equal to 0. So mu is defined on a collection C of subsets and we want the properties that empty set should belong to C, mu of empty set should be 0 and mu on this collection should be countably additive. Such a set function is going to be called a measure on C. Let us look at some examples of set functions. So let us start with a very simple one. Let us look at a set X which is a countable set. So its elements are x1, x2, x3 and so on. So x is equal to xn, n 1, 2, 3 so on. And let us fix Pn a sequence of non-negative real numbers. So X is a set which is a countable set with elements x1, x2, x3 and so on, and we are fixing arbitrarily some sequence of non-negative real numbers. So let us define for any set A contained in X, for any subset A contained in X, let us define mu of the empty set to be equal to 0, and for the set A, if it is non-empty, let us define mu of A to be equal to summation over those pi's such that xi belongs to A. So A is a subset of X, so some of the xi's will belong to A. So look at those indices I such that xi belongs to A. Pick up those pi's from this given sequence Pn and add them up, and that is called mu of A. So mu of A is defined as summation over those pi's such that xi belongs to A. We want to check that this is a measure on the collection of all subsets of the set X. Well, that is quite obvious because mu of empty set is defined to be equal to 0, and let us observe that mu of the singleton, if A is a singleton set, then mu of the singleton set is going to be the number pi. So if a set A is a countable disjoint union of sets, so let us check that this mu is a measure. So we are defining mu of A to be equal to summation pi, where I is such that I is such that xi belongs to A. So mu is countably additive. So let us take a set A. So let us take a set A which is union of AI's, I equal to 1 to n, AI is belonging, AI a subset of A, subset of where AI is any subset of X. To check that mu of A is equal to AI's belong to, and we want that AI intersection AJ to be empty. So we want this to be equal to mu of AI's I equal to 1 to infinity. Let us observe enough to check when each AI is a singleton xi. Okay, so let us check that case first. So what is A? A is let us when AIs are some not xi, let us because x itself is x1, x2, xn, so this will be the whole space. So let us look at the special case when say AI is equal to some xki, I bigger than xki, I bigger than or equal to 1. Then the set mu of A is going to be equal to summation p of ki, I equal to 1 to infinity, which can be written as limit n going to infinity of n going to infinity I equal to 1 to infinity pi up to n. So sum of a series, these are non-negative numbers, so this sum is nothing but the limit of the partial sums. Okay, they are non-negative, so there is no problem in writing it that way. So that means mu of A is equal to limit n going to infinity of sigma I equal to 1 to n of pi. Okay, but that means what we want to check, that it is summation of mu of each AI. So this is limit n going to infinity of summation I equal to 1 to n mu of AI, because each one is pi p of is p of ki, sorry, this is summation p of ki, so this is ki and this is mu of AI, so that is equal to I equal to 1 to infinity mu of AI. So mu of A is equal to summation mu of AI's whenever AI is a singleton set. If not, it is a finite set, then each finite is a union of finite sets, and then because for a non-negative series you can add it in any way you like, it's easy to check that mu of A is also equal to, so it is easy to check that mu of A is equal to summation mu of AI I equal to 1 to infinity whenever AI's are contained in X and AI intersection AJ is empty. So that says that this set function mu that we have defined is countably additive. So this is what is called a discrete measure because it is given by a sequence, and pi is called the mass at the point xi. So as we observed, mu of the singleton xi is equal to pi for every I, and mu of the whole space, which is equal to summation mu of the singletons that is pi. So mu of x is equal to summation of pi's. So obvious consequence of this is that mu of x is finite whenever this series is convergent. So the mu is, one says this discrete measure mu is finite, that is mu of x is less than infinity, mu of the whole space is finite if and only if summation mu of pi is less than infinity. If this summation of pi is, if this series pi is convergent and the sum is equal to 1, then this measure mu is called a discrete probability distribution on the set X, which is x1, x2, xn. A very special case which plays important role in the theory of probability and so on. X is the set of the numbers 0, 1, 2 and so on. Let us fix any number p which is between 0 and 1 and define pk to be equal to n choose k. So this is the binomial coefficient n choose k, p to the power k 1 minus p raised to the power n minus k, k between 0 and n. This is called the binomial distribution because of this binomial coefficient appearing in the definition of pk. And it's quite easy to check the summation of these pk's is equal to 1. That is, because summation of the pk's is summation k equal to 0 to n, and this side is nothing but the sum is equal to of p plus 1 minus p raised to power n, and that is equal to 1. So this is a distribution which plays a very important role in probability. This is a probability distribution. Supposing you have got a coin and you are tossing a coin with probability p for head appearing, then in n tosses this pk represents the probability that in n tosses you will get k heads. Another special case of this discrete distribution is called the binomial distribution, is called the Poisson distribution, which is characterized by the definition that pk is equal to lambda to the power k e raised to power minus lambda divided by k factorial. This is called Poisson distribution. This is another important distribution in the theory of probability. And finally, when we take only the finite number of points 0, 1 up to n and pk is 1 over k, then each point is given the same mass 1 over k, then this is called the uniform distribution. So there are special cases of discrete probability distributions. Next we give an important example of a measure which is defined on the collection of all intervals in the real line. So to do that, let us fix our notations. So we will denote by I the collection of all intervals on the real line. For an interval I with endpoints a and b, the left endpoint being a, the right endpoint being b, we will write it as I a comma b. So a will denote the left endpoint and b will denote the right endpoint. We are not saying that this is an open interval a comma b. We are just saying that it is an interval with left endpoint a, right endpoint b, where the left or the right may or may not be, or both may or may not be included in that interval. So it is just an interval with endpoints a comma a and b. Left endpoint is a, the right endpoint is b. So on this collection of all intervals, we are going to define a function. So for example, recall that the open interval a comma a is the empty set, and the interval 0 to plus infinity. So the square brackets indicate that we are including 0 and we are including plus infinity. So this is the closed interval in R star, x belonging to R star, the extended real numbers x bigger than or equal to 0, which is same as the open interval, closed on the left 0, open on the right infinity. In the real line union, the special symbol plus infinity that we had added in the extended real numbers. So with these notations, we define what is called the length function on the class of intervals. So it is a set function lambda defined on I, taking values in 0 to infinity, and is defined by, take any interval I with left endpoint a, right endpoint b. So we define it as the absolute value of b minus a if a and b are both real numbers. That means if the interval I is a finite interval with endpoints a and b, then its length is defined as b minus a. And we define it equal to plus infinity in case either the left endpoint a is minus infinity or the right endpoint b is equal to plus infinity, or both. So length of I for a unbounded interval is defined as plus infinity. So this function is called a length function on the class of all intervals, and this length function is going to play an important role for in our subject. So let us study its properties. So next we will be studying properties of this length function. The first property is the length function has the property that lambda of the empty set is 0, because empty set is an interval is an open interval with left endpoint say a, right endpoint a. So both is open interval a comma a, which is empty set. So by very definition, that is equal to a minus a, which is equal to 0. Next, let us check that this is a monotone set function. So namely, length of I is less than or equal to length of j if I is a subset of j. So to prove that, so we want to check whenever you have got intervals I comma j and I is a subset of j, this should imply that length of I is less than or equal to length of j. Since the intervals are defined characterized by the endpoints, so let us case 1, let us say I is say infinite, say I is equal to minus infinity to say a. Let j be equal to, now since I is a subset of j, obviously j has to start with minus infinity and it can go up to some point say c, where c is bigger than or equal to a. So essentially what we are saying is, if this is a and this side is the interval and this side is the interval, all of it is the interval I, and if j is to contain I, then j must be somewhere ending somewhere here, so that is c. So clearly both are infinite, so length of I is equal to plus infinity is length of j. So that case is obvious. Let us look at the next case. I is a subset of j, j is infinite. Whether I is infinite or not doesn't matter, because the length of I is always less than or equal to plus infinity, which is equal to length of j. J being infinite, its length is always going to be plus infinity. So this is obvious if this is the case. So finally let us look at the case when both I and j are finite. So here is, so let us say I has got the endpoint a and b. Now I is subset of j, that means the endpoints of j has to be somewhere here and has to be somewhere here. So if I is with endpoints a b and j is with endpoint c d, then we should have c is less than or equal to a, less than or equal to b is less than or equal to d. So this implies this, and that is same as saying that d minus c is bigger than or equal to b minus a, and that is saying that the length of j is bigger than or equal to length of I. So the monotone property is checked. So the length function lambda is a monotone property, namely if I is a subset of j, whenever interval I is contained in another interval j, length of I is less than or equal to length of j. Next, let us look at another property is called finite additivity property. So what should be finite additivity property? We want whenever an interval I is a disjoint union of some other intervals, then the length of I should be summation of length of j's. So what we are saying, if a interval I is written as a finite union of intervals ji 1 to n, where these ji's are pairwise disjoint, then we want length of I to be equal to length of summation length of gi's. So that is going to be called the finite additivity property. So let us check the finite additivity property. We want to check if I is equal to union of ji's, all are intervals where ji intersection jk is empty, then that should imply length of I is equal to summation length of ji's, I equal to 1 to n. So let us assume if I is infinite and I is equal to union of ji's 1 to n, then that implies at least one of ji's is infinite, because if all of them are finite intervals, their union will be again a finite interval. So I infinite implies I equal to union of ji's implies at least one of these ji's has to infinite, so that implies lambda of I is equal to plus infinity is equal to summation lambda of gi's I equal to 1 to n, because one of them is plus infinity. So the case when I is infinite is okay. Let us look at the case when I is finite. So I finite, I equal to union of ji's, and ji's are pairwise disjoint. Now let us say the interval I has got endpoints A and B, and let us say the left end point is A, the right end point is B. So here is A and here is B. We want to compute the length of I. So note, length of I is same as the length of the closed interval A comma B. I can include the endpoints in the interval I, because the length depends only on the values of the endpoints. It does not matter whether the endpoints are inside or not. So what we are saying is, without loss of generality, let I be equal to A comma B. Okay, so this is the interval A comma B. Right. Now I is equal to union of gi's. So the point A belongs to this union, so it should belong to one of the intervals ji's. Okay, so it belongs to one of the intervals ji's, and actually it has to be endpoint of one of the intervals of ji's, because the interval cannot start with somewhere else. So let us say, so without, we can say, we can assume I1 the interval J1 is starting at A and ending somewhere, let us call it as B1. Okay, the point end point may or may not be included. So the first interval I1, we can assume it starts here and ends somewhere here, that is B1, right? Now the point B1 is again in that union. So either it is already included in the interval I1, or it should be an endpoint of another interval in the union J1, J2, Jn's. So the second one must start with here and end somewhere here, that is B2. So what we are saying is I2, some other interval, we can rename it as I2. So it should start somewhere again at B1 and end somewhere here, and so on. So here will be the last one, AN, and that should be BN. So what we are saying is, we can assume this is, so going this way, we can arrange the endpoints of J1, J2 and Jn such that A is same as A1, less than or equal to B1, is equal to A2, less than or equal to B2, and so on. So AN less than or equal to Bn, which is equal to B. So we can rearrange these endpoints of these intervals, because this is a union and that is a disjoint union. So this is what is possible for us to arrange. So that means, and that clearly says that B minus A is equal to Bn minus A1, that is equal to summation Bi minus Ai, I equal to 1 to n. Adding and subtracting these terms in between, that is same as I equal to 1 to n lambda of gi. So whenever I is a finite interval, I is equal to union of gi's, they are pairwise disjoint. We have gotten that the length of this b minus a is the length of the interval I is equal to summation length of gi's. So that means that the length function lambda is finitely additive. So this is the property of lambda, the length function being finitely additive, namely if an interval I is a finite union of pairwise disjoint intervals, then length of the interval I is equal to summation length of gi's.